Human beings are not all the same height. An astonishing fact, I know. Imagine if they were though. First of all, it would be super weird. But second of all, so would the graph.
She needs to sort out her priorities.
If we plotted a frequency distribution chart of the heights of a large sample of people in this fictional world where all human beings are the same height, it would look like this. Not a particularly interesting chart. This is fictional though, believe it or not. So what does it actually look like in the real world? Well, something like this. I've downloaded this data set from Kaggle, and we'll include a link in the description if you would like to do the same. But when we plot out the frequency distribution chart and filter the data specifically for female heights, we get this really nice shape. We can do the same thing for male heights too, or both at the same time, but either way, it's got a really notable shape to it. Often called a bell curve because, well, it's shaped kind of like a bell. It's a fairly common distribution that comes up in all types of data sets, like human heights. Just looking at the graph, what are some other characteristics that you notice about it? One of the first things that I notice is that it has a really nice symmetry. If we drew a line down the middle, it's like a mirror image on either side. It also kind of tapers off towards each side, right? Like the middle has a large frequency, and as you move further away to the left or right, it gets closer and closer to zero. Thinking more about the middle, you might recall some specific statistics that we commonly use, like mean, median, and mode. Well, in a graph like this, the mean, median, and mode are all the same value. This value, marked with the line down the middle, is the middle value, so it's the median. It's also the most common value, so it's the mode. And since the data is symmetric on both sides, if we were to add everything up and divide by the total number of elements, well, that would show us that it's also the average. In statistics, those are some pretty important traits. And this type of distribution comes up commonly enough and is important enough to be worthy of a special name, the normal distribution. To be a bit more precise, the normal distribution is characterized by the following properties. As we noticed already, the mean, median, and mode are the same value. It's also symmetric about this value, as we saw already too. One thing we can't necessarily observe just from looking at the graph though, but is a critically important criteria nonetheless, is that the area underneath the curve is equal to 1. Yeah, so you know how in geometry you computed areas of different shapes? Like the length times width gives the area of a square, or pi r squared gives the area of a circle? Well, it turns out there is some really fun and interesting calculus that allows us to find the area of almost any shape, including this bell shape. Now, that is a whole nother topic for weeks of discussion in a calculus class, so we won't go into detail here. But for our purposes now, know that to be a normal distribution, the area here in blue, under the curve, that must equal 1. It's also asymptotic on both ends. What is asymptotic? Maybe you've heard that term before in a previous math class too, but if not, think of a graph like the one of 1 over x. As we look to the right, this line gets really, really close to 0. Closer and closer the bigger the value of x is, but it never touches. So similarly, for the normal distribution, as the curve moves further and further out to each side, away from the mean, it gets closer and closer to 0, but will never be 0. It never quite touches. Finally, and this is a subtler point, there's a point along this curve where the curve of the curve kind of changes direction. I know that was not my most articulate point ever, but hear me out. If I start to draw this curve, as the line moves upward, you can see the inside of the curve here is above it. I can change this though while still moving upwards. So the inside of the curve is now facing downwards, right? Here it's above the line and here it's below the line. That's the same as what's happening in our normal curve. The curve changes from curving upwards to curving downwards, even though the values are still increasing overall. This is known as an inflection point. And specifically, for a normal distribution, the inflection point will occur 1 standard deviation to each side of the mean. So this value will be the mean minus 1 standard deviation, and this value will be the mean plus 1 standard deviation. Which does mean we have to be careful sometimes, because any generic bell shape doesn't necessarily imply a normal distribution. A normal distribution has to specifically meet each of these criteria. Now, one cool implication of this is that the normal curve can be entirely determined by just the mean and the standard deviation. If we compute these for our female heights from the data set, we get a mean of about 150 centimeters and a standard deviation of about 11 centimeters. So with a quick little adjustment to our code to input these values, we can plot the true normal curve with the same mean and standard deviation. And as we should expect, it matches our data almost exactly. Now, if our data is based on real world data, it's not likely going to match literally exactly, but this is pretty darn close. Let's dive a little deeper into how we can plot that curve though, particularly given the values of a mean and standard deviation. Specifically, we can use this formula. Y is equal to 1 divided by the standard deviation times the square root of 2 pi times e raised to the negative x minus the mean squared divided by 2 times the standard deviation squared. That might look kind of crazy at first glance, but honestly, don't get too caught up in the specifics for now. Understanding why this formula describes the normal distribution, that's a discussion for another day. For now, let's just observe that it does. If we come over to Desmos and type it out, setting values for m and s to represent our mean and standard deviation, we can see the plot of our normal curve. I'll put a link in the description so you can access the graph too, because it will be useful for a few things coming up shortly. Now, this graph is specific to our data on female heights. If we wanted to change it to reflect a different data set, we just have to update the values for the mean and standard deviation. Then the graph would change to reflect that. Because there is an infinite number of values that we can plug in for these, it often helps when working with these distributions to standardize them. Specifically, we'll look at the normal curve with a mean of 0 and standard deviation of 1 and refer to that as the standard normal distribution. If you recall what a z-score is, one helpful thing about using this standardization is that the values along the x-axis represent z-scores. But truthfully, that really buries the lead. In fact, this entire video so far has really buried the lead because the coolest thing about all of this is not just the pretty symmetric bell shape, or the possibly scary looking formula that can produce it, or the connection with z-scores even. Rather, this is profoundly powerful because of what it says about probability. What do I mean? Well, it turns out that the area under this curve, and more specifically the area under any particular slice of this curve, represents the probability of selecting a value in that interval. So for example, we might ask a question like, if we chose a random human female from our data set, what is the probability that she is shorter than the mean, shorter than 150 centimeters? Well, 150 centimeters lives here on our graph. So this question is equivalent to asking, what is the area under the curve to the left of 150 centimeters? Or, what is the probability of selecting somebody taller than 150 centimeters? That'd be like asking, what is the area under the curve to the right of 150 centimeters? Or, what is the probability that we'd select a human female between 160 and 170 centimeters? That would be equivalent to asking, what is the area under the curve between these two values? Now, I should note here that at this point, most statistics classes or statistics textbooks will show you a bunch of crazy looking tables and explain that to find these probabilities, you gotta convert everything to the standard normal curve and then scan the table based on the z-score, and honestly, whatever. Those tables were for the cool kids back in the day when people still had to carry around giant books to look up definitions of words. We now have computers in our pockets, so forget the dusty tables, we're not gonna use them. Instead, there are a variety of different ways to compute this using various calculators, Excel or R. Since we already have Desmos open and the template in the description is designed to make this as simple as possible for you, let's start here. If there are other tools you'd like me to demo in the future, let me know in the comments. Once you open up the template, you'll see that the expressions for the normal curve and for computing the area underneath are already included. So only mess around with those at your own discretion. All you need to do is to plug the value for your specific mean and standard deviation. This will then plot the normal distribution. Then change the upper and lower bounds, U and I respectively, to match the region you're looking for the area of. For example, if we plug in a mean of 150 and a standard deviation of 11, the plot might disappear at first, but that's okay. Look at our axes. Our mean is 150 and we're maxed out around 5. So with a bit of resizing our window, we can find the curve and see our graph plotted out nicely. To answer our questions, we'll determine the upper and lower bounds. For example, the probability that we select someone between 160 and 170 would mean we plug in 160 for L and 170 for U. You can see this highlights the region on the graph, which is a helpful visual to confirm we're actually answering the question that we set out to ask. The value that it presents here, in our case about 0.147, is the area under the curve between the lower and upper bound. So the probability that we'd select someone between 160 and 170 centimeters is about 14.7%. For any question that has only one bound, like what is the probability that we'd select somebody less than 150 centimeters, we can use infinity as the bound. So here, our upper bound would be 150 and our lower bound would be negative infinity. And yes, we can just type out the word infinity and it will figure it out. This gives us a probability of 0.5, which, if you think about it for a sec, that actually makes a lot of sense because remember, 150 is our mean. 150 is our mean, yes, but in a normal distribution, the mean is also the median and the mode. And to be a median, it means you are the middle value, or in other words, you're greater than half of all the other data points. If we flip it to greater than 150 centimeters, we'll see we get the same. And of course, if we span the entire curve by setting both bounds to infinity, we get an area of 1, which, if you remember, is what we said the full area under the curve had to equal. So this is pretty powerful. If we have a data set that is normally distributed, we now have the ability to compute the probability of selecting any range of values from it. That is just the beginning when it comes to the power of the normal distribution. But hopefully you found this video helpful so far. Let me know if you have any questions, and as always, have a great rest of your day.